So now let's talk about the serial communication. So as I explained earlier, I need to use two Arduinos. So I had to split the responsibilities between them. So this one, we are going to call it the UX Arduino, is in charge of all the user experience. So it's in charge of handling the touch data when the user draws something, and it's in charge of drawing things on the screen. So when I draw a line like this, it's all handled by this Arduino. So if I choose a different color and draw something, all this is handled here. So if I disconnected the two Arduinos, it would still work to draw things here. But of course, it would not transmit them to the other station like this. So basically, when I'm drawing something, what really happens is that the touch data goes to this Arduino. Then it sends back some instructions to draw something on the screen, but it also sends some data, which are basically the coordinates of the new line which has been drawn, to the Wi-Fi Arduino here. And this Arduino is going to transmit them to a Redis server which is online. And then on the other side, the other station has just the same two Arduinos. So in that case, the Wi-Fi Arduino is going to get the data from Redis on a subscribe channel, and is going to send them via a serial connection to the UX Arduino, which is going to draw the lines on the screen like this. So the serial communication is very important in all this. So let's explain a bit how it works. So let's explain the serial protocol I have created. So first, there are 4 types of messages. So the first type of message is simply an alive message, which is there to tell the other Arduino that we are still working. So each Arduino in a single station is telling the other every second that it is properly working. Here it's an alive packet, so there is an A to say that it's an alive message, and then there is nothing. These are just nulls because there is no content in such a message. The second type of message is a clear message. So it's when you press the clear button, which means to clear the drawing. So here you can see that it's pretty much the same, except that there is a C instead of an A. And then the third type of message is much more interesting. It's when you draw a line. So when I'm drawing a line like this, you can see that there is quite a lot of data transmitted. And you can see that there is first an L for line, and then there are 8 bytes, which are the coordinates of this new line. And the last byte is actually the color. So let's put that in X so it makes more sense. So here it's color number 4. So if I change the color, so it's color number 4, 0, 1, 2, 3, 4. So if I select, for instance, so if I select red, then it's going to be color number 5, color number 6, sorry, and here you can see that there is a 6 at the end of every new created line. And the last type of message are the status messages that are displayed right here. So in this case, it's not symmetric. These messages are only transmitted by the Wi-Fi Arduino to the UX Arduino for display right here. The UX Arduino is also able to decide to display a status message. It can also do that, but in that case, it doesn't need to transmit this information to the other station because these are only messages for diagnosis locally on a station. So there is no point in transmitting them online. So these messages, they look like that. So here you have an M-like message, and then you simply have an ASCII string. So as you can see, the message is incomplete because it's transmitted in several packets. We are going to explain why in a few minutes. So now let's talk about the real problem I had when I had to implement serial communication. So one of the difficulties here is that while the Wi-Fi Arduino is transmitting data to the online server, it cannot do anything else because there is no multitasking on an Arduino. So while it is sending the data to the Redis server and waiting for the response, it cannot take care of receiving the serial data that is being transmitted by the UX Arduino. And this amount of data is significant because it is around 500 bytes per second. So you might think that the first solution would be to wait for all the drawing to be finished and then to transmit the complete drawing, but this is completely impossible because it would be much too big, so we cannot retain the entire drawing in memory. Even with the bigger memory in the Wi-Fi Arduino, because on an Arduino Uno you have 2 kilobytes of RAM, and on a Wi-Fi Arduino you have 6 kilobytes, so that's much better, but that's still not enough to store a complete drawing. So you have to transmit the drawing, you have to send it online while it is being drawn. So this means that there are some packets which are transmitted over the internet while I am drawing a line like this. So the question is then, how can we handle the pixels and the lines being drawn while we are transmitting data? So a first solution would be for the UX Arduino to keep the data while the Wi-Fi Arduino is busy transmitting them online, and then when the Wi-Fi Arduino is ready again to receive some new data, it would tell the Wi-Fi Arduino to send the data over. So that could be a possible solution, and if you have seen my previous video about the music played from floppy disks, it's actually what I have implemented. But here this is not a possible solution because the memory in an Arduino Uno is too small to hold the data for long enough. It would be able to store like 1.5 seconds of data, which is not too bad, but if the transmission is a bit slow, this can be too little. So the solution I have chosen is to instead use an interrupt. So actually I said that it's not possible for an Arduino to do multitasking. That's not completely correct. There is a possible way to do that. It's to use interrupts. So while we are transmitting the data to an online server, basically we are executing a line of code like send bytes or something like that. But if an interrupt is triggered, we are able to execute a small function called an interrupt service routine, or ISR, and we can use this to record the serial data which has been transmitted. The serial data is actually stored on a very small buffer, which is called a UART, and it's able to store 64 bytes of data, which is very, very small. So when some packet is transmitted, we need to store the data to RAM, which is much bigger, to be able to make space for the next packet in the UART buffer. So how does it work? So basically, to transmit data from the UX to the Wi-Fi Arduino, of course we have a wire to transmit the actual serial data, but I have added a second wire here, which is used for an interrupt. So what basically it does is very simple. When it has transmitted a packet to the UART buffer on the other side, it's going to trigger the interrupt service routine by pulling high and then pulling low the voltage on this wire, which is the interrupt wire. So here is what it looks like on the oscilloscope. So you can see that here, this is the serial data that is transmitted. Then on the interrupt wire, it goes high and then it goes low 1 millisecond after. This is to let the receiving UART store the data in the buffer so that we are sure that here the data is ready to be read from the buffer by the Arduino. And here this is the interrupt service routine running time. So you can see that it's very fast actually. So what it does here is that it copies the content of the UART buffer basically in the buffer in RAM. So this is very, very fast, and you can see that when I'm transmitting data, we can look at the bigger picture. You see that there is plenty of time to run other operations than the ISR. So now you might wonder, how does it work in the other direction? So in the other direction, it's actually much simpler because this Arduino is never going to do very long operations. So basically, it can run the main loop a lot of times per second, and it's never going to take much longer. So the only thing we need to ensure is that we don't put packets too near to each other, in which case it would miss some data. So the trick is basically here just to wait 10 milliseconds after transmitting each packet. And there is a second thing to take into account, is that we need to transmit these status messages. And as you can see, these status messages can be longer than what you would expect on a packet. So basically here you can actually write 100 characters. But as I have shown you earlier, the packets are actually smaller. So why is that? It's because you cannot transmit a packet of 100 characters because it would exceed the size of the UART buffer. So you might say, well, why not choose a packet size like 50 bytes or something like that? And why choose something that small? Actually, the reason is to allow for some margin when the data is transmitted. If it's not read immediately, then we want to have at least the margin to be able to store one extra packet in the buffer. So I have decided to put smaller packets like that. And actually here you can see the beginning of a string, which has it's written trying to something. It's the beginning of a status message. And here you have M like message. And here actually this value is an offset, which indicates which part of the message it is. So in fact, when we are transmitting a message, we transmit several packets. And here this ID allows to know whether it's the first, second, third, etc. packet, and then they are concatenated together, and when the full string is arrived, it's displayed on the status bar right here.